Hi, and welcome to the Space Industry podcast by satsearch. My name is Narayan, COO at satsearch, and I'll be your host as we journey through the space industry. The space sector is going through some seismic changes, promising to generate significant impact for life on Earth and enable humans to sustain life elsewhere in the cosmos. At satsearch, we work with buyers and suppliers across the global marketplace, helping to accelerate missions through our online platform. Based on our day-to-day work supporting commercial activity, my aim here during this podcast is to shed light on the boots-on-the-ground developments across the globe that are helping foster and drive technical and commercial innovation. So come join me as we delve into a fascinating, challenging, and ultimately inspiring sector. In today's episode, we'll be talking about stray light and how it affects different optical systems and their performance on board of satellites. We have with us Dr. Tamas and Narayan, research and development engineer with extensive experience in the field of composite materials and structures, who is the materials and mechanical lead at Acktar. Acktar itself is a technology leader in development, industrialization, and production of light-absorbing black coatings based on vacuum deposition technologies. Tamas, thank you so much for taking the time for recording this podcast episode with us. Welcome to the Space Industry Podcast.
Thank you for having me, Narayan, and let's get right to it.
Great. So today we're actually talking about stray light. This is a kind of a unique problem because of the light sources that are existing in space and the impact on that on making satellites work better. So can you just tell our listeners what exactly is stray light and why does it actually cause problems?
Yeah, of course. So do you like taking pictures? Because I do. Have you ever had a picture when, it came out like dazzled or too bright, or like you had these marks, kind of round white marks around it? That's stray light. Stray light is basically any light that enters like an optical system from a source that you didn't invite in. And it disturbs the image quality simply. It can be a reflection from a mechanical part itself, a reflection between the optical components, or it can come directly from the sun, like an external source, outside its intended field of view. And the bottom line is that it really significantly reduces the contrast of the image that is developed. This is really important in space applications. So if you're talking about, let's say, star trackers, which are essentially like GPS systems of satellites, they use stars to orient and position themselves. And basically, stray light can wash out the image so much that the system will not recognize where it's pointing. So when we talk about star trackers, they are very sophisticated measurement systems, and they help spacecraft and satellite to determine the exact position and the orientation in space by taking pictures of the stars. And it analyzes the angles between them, which are called or referred to like azimuth angles. And if these devices are compromised by stray light, then the measurements can become noisy, full of errors, and it will lead to incorrect positioning and orientation data. What it means, it can be jeopardizing the whole entire space mission. So there is a lot of methods engineers and industry has been trying to counter this and mitigate this using vanes, buffers, shields, coatings to prevent any unwanted light from entering these systems or star trackers. And this is where we Acktar come into play, because we manufacture fully space qualified coating solutions, which basically absorb, I would say, almost 99% of stray light on the entire electromagnetic spectrum.
From what I gather from what you said, it's mostly trying to bring clarity to the eyes of satellites at the end. And essentially, there are three things that come to my mind. Obviously, star trackers and sun sensors and possibly cameras. Are these the three main devices that are affected by stray light, or on other parts in a satellite as well?
I would say it's mostly any optical system that has any kind of sensor that does any measurements, basically. These are the key components. But when we talk about stray light and, let's say, for example, Acktar coatings, they have much more than that, much more function than that. Basically, one of the key applications is to absorb stray light But also our coatings at Acktar, they protect against atomic oxygen that can erode the material itself. And we can tailor the coatings solar absorptivity or infrared emissivity ratio to provide different passive thermal management solutions. What it means that, let's say, imagine you have a satellite going close to the sun, and you need to make sure you have enough heat dissipation to cool down the satellite. So we can do and help with that. If you go to deep space where it's really cold cryogenic temperatures and you need to keep or maintain thermal stability, then we can also help with that by absorbing and retaining all the heat that is possible in the satellite.
There are these kinds of different scenarios that you talked about. And, there are, obviously, you said it's all about optical systems out there. Are different types of coatings then applied differently for different optical systems, or are they different also for like LEO, GEO, and interplanetary scenario?
Yeah, I mean, absolutely. Mission environment presents unique stray-light challenges. So I have a couple of examples in mind. So solar illumination, near sun missions, in the inner solar system, or bright body missions like Mercury, they face very intense light and they risk sensor saturation. So very robust shielding and coatings are really essential for stray light suppression. Then you have thermal extremes, so wide temperature swings that misalign optics. So materials can expand or contract, right? And stray light mitigation systems, they must be not only optically effective, but thermally stable, as I mentioned. So Acktar coatings, for example, they are currently qualified between minus 290 to plus 450 degrees Celsius. But we have we have a coating called Fractal Black, which has gone or seen much higher temperatures than that for shorter periods of time. Then we have, there are surface reflections. So if you go icy moons or bright surfaces like salt flats on Mars, they reflect light at very sharp angles, and these reflections often act as a secondary light source. So to mitigate this, for example, anti-reflective coatings, or called AR coatings, or spectral filters are used. And we also have certain products in our portfolio that absorb stray light at these grazing angles. So for example, Lambertian Black, it's a very thin coated film, especially made for that. Or we have Hexa Black, which is not a standalone product, but is very well used in combination with a black or dark background. It's basically a commercial aerospace grade aluminum honeycomb, and it really takes stray light suppression to the next level because it absorbs light with an angle of incidence up to 88 degrees. So this has been used very widely in baffles and telescopes to replace traditional vanes. And this way, it will reduce the manufacturing cost and the overall weight of the structure while keeping the optical performance. We also have dust and particulates. So many planetary missions, especially where you have rovers or landers, they deal with dust on the surface or in the atmosphere, and this can accumulate and degrade the image quality and increase the stray light contamination. So there are a lot of active and passive cleaning mechanisms that are used for this. We also test our coating's durability against, let's say, lunar regolith to support such missions. Then if you look at deep space missions, they require lightweight and very compact solutions. And Acktar's really ultra-thin coatings, they provide an all-in-one solution, not only the high performance with minimal mass, but also they provide the resistance to the space environmental conditions, which is really critical. Then you can look at mission goals, right? So you have a science mission, which will have obviously different needs to, let's say, a faint object astronomy. They will demand stricter stray light control than a bright surface imaging study, where it looks at surface geologies, for example. Then, just to mention as last, dynamic lighting. So rovers and fast orbiting probes, these are orbiters flying around rapidly rotating planets. They face these very changing, shifting light conditions. So an adaptive stray light mitigation and exposure control are really key. So to summarize for everyone, every mission demands a tailored stray light mitigation strategy. And in deep space, the background is pitch black. You have to worry about sunlight sneaking in or bouncing internally. thermal stability and long-term durability is what really matters here. On planetary missions, you might be dealing with bright surfaces like Jupiter's clouds or Mars's dusty landscape. It can flood your instrument with reflected light. So that's where angular control and spectral properties of coatings come into play. But at Acktar, we work with engineers really early on to model all of this and tailor the coating to the choice for each environment, basically.
Right. You had something very interesting to say, especially on the legacy techniques and the coatings. I want you to briefly explain the legacy veins that were used versus the coatings. How much is the difference in optical performance when you compare the both?
So this is very interesting. This is where optical design and optimization comes into play early on in the process. So it's very important to understand that, let's say, a smart optical layout would start with strategic placement of lenses, apertures, mirrors to minimize the likelihood of stray light path that can reach the sensor. And there's a lot of proper ray tracing and simulations during this design stage to eliminate problematic geometries before anything is even being built. In this phase, you will make sure that you have veins just to the right amount, not too restrictive, not too extensive, that will let just enough light in that will give you the desired amount of data, information, or quality, what you're looking for. In this stage, our coatings, so Acktar, we have BRDF data available for our coatings. What it means, BRDF is a short term for bidirectional reflectance distribution function. It's basically a function that defines how light is reflected off an opaque surface. You might ask, okay, what is an opaque surface? So an opaque surface, it doesn't let any light pass through. It means that whatever light comes in, it will either get reflected or absorbed. And this data is very, very helpful and useful in design when you input it into the simulation, and it can really give you the performance. So, for example, if you only have veins or coated veins, or you have only coatings but no veins, you can really compare the optical performance in these simulation tools. Now, Acktar has BRDF data for almost all of our coatings, and it is integrated in and available in various stray light simulation softwares. So one of the most well-used is Zmax, FRAD, Synopsys, TracePro, and these tools are really critical to ensuring accurate optical design and optimization.
Right. So let's assume that I am a manufacturer of a star tracker or a sun sensor, or, for example, I am building a camera for my own Earth observation satellite. At what point in time would I be coming to you as the expert in stray light, and at what point in time should I be coming to you?
I would say that you should come to us from the beginning. Stray light control involves not only design, but also hardware and software strategies to make sure that you have the right mitigation strategy, and it can be applied throughout the product lifecycle. So we talked about optical design and the optimization part, but you can discuss with optical engineers and stray light mitigation techniques when it comes to buffers, field stops, lens hoods. You can go to suppliers who deal with anti-reflection coatings. These are applied on lenses and transparent components to reduce internal reflections. And actually, for the sake of the audience, Acktar black coating is very compatible with anti-reflective coatings. So you can coat on top of Acktar black, and it does not influence the optical performance. So it still looks black and very low reflectance under. If you're looking at blackening internal surfaces, that's when you really come to us, I mean Acktar, because using ultra black coatings on internal surfaces and walls, it absorbs the stray light and minimizes internal scattering. And this is where we contribute significantly, because we offer really high performance ultra black coatings that provide the performance and stability even in harsh environments. Then, you can also place certain software AI solutions, algorithms in place to contrast enhancement or background subtraction to clean up stray light artifacts. It's not replacement for hardware generally, but it's very helpful layer to overall stray light mitigation. So really, stray light mitigation is a combination of clever design, specialized materials, and even smart software. There's really no one-size-fits-all solution, and it's about layering multiple strategies to meet the specific needs of each mission.
We briefly touched upon the types of mission. There are obviously different types of missions, right? There are low Earth orbit, or today even very low Earth orbit, where maybe there's many more things that affect lenses and other things. And then there is the geo missions and then interplanetary missions. Are there different design choices or even coating choices based on where people are going, where people are operating, and what environment that they are in? You briefly touched upon that the coatings are meant to work in different thermal environments, but when it comes to the performance and the design, can you briefly touch on these aspects?
Yeah, so as I mentioned before, we have, for space applications, Acktar coatings, they have 3 key functionalities. So let me just repeat that. We absorb stray light 99% from deep UV through visible to far infrared. And this is one of the key advantages. We make sure that, let's say, your star tracker is protected against atomic oxygen, and we can tailor the solar absorptivity and infrared emissivity ratio of the coating. Now, you need to know that we have a lot of products available at Acktar, or Acktar brands that we offer, and all of our black coatings are similar, but they are specifically designed and tailored to a specific wavelength of interest or to the application itself. With that, I actually would like to give 2 examples of our most popular coatings in space applications and how they kind of help these different missions. So we have Acktar Magic Black. Acktar Magic Black is it's a coating that is applied on 3D complex star tracker baffles and almost on all European star tracker manufacturers' products. It is extremely black. When I say extremely black, it means it's roughly about 1.2% total hemispherical reflectance. And this is the measured meant for how reflected the black coating is, and exactly designed for the operational wavelength of star trackers. So star trackers, obviously, the wavelength ranges from 400 nanometers to 1,000 nanometers, which covers the visible and a bit on the near infrared end of the spectrum. Magic Black has very high emissivity, so it can dissipate heat very effectively, and it allows for efficient thermal management of the space instrument. And it's very, very thin, just about 3 to 5 microns thickness. And you can really customize it to the accuracy of a few microns when it comes to sharp edges or knife edges in optical systems. So vanes, for example. It's resistant to ATOX, radiation, extremely low outgassing, and qualified for all specific substrates that are typical for star trackers. Usually, these star trackers are very common in low Earth orbits where, you have satellites orbiting Earth and giving communication to all kinds of applications. Magic Black has a really extensive space heritage. I'm just going to name a couple of them. Basically, James Webb Telescope, Bepi Colombo, Flex, JUICE, and even on board of the International Space Station. And I want to emphasize that at Acktar, we can provide the high performance, but we can do this in high volume. So if you need, we can deliver up to even 1,000 units per month, including a capability for build to print. So we can manufacture and coat it as a service. And we also offer components, coated star tracker or telescope baffle components, such as vanes and barrels that are available from our catalog items. Another coating I really want to mention called Acktar Fractal Black. It's truly one of our most popular coatings for space applications. And if I'm correct, it has about 43 missions to date that has been used on. And one of the most famous projects at Acktar that was using Fractal Black was the near-spec instrument on the James Webb Telescope. It not only provides the extremely low reflectance, but it does it at a really broad band spectrum. So really covering a wide range of the electromagnetic spectrum from UV to far infrared. And it's much more durable and has extremely high emissivity. So even compared to Magic Black, it has higher emissivity. The thickness of it is about 5 to 14 microns, and it's also highly customizable. So we can tailor it to the mission needs, basically. what I want to say is that Acktar Magic Black and Fractal Black, they are really great examples for these space applications. They are used differently and for different missions. So Magic Black, again, it's really one of the most popular for star trackers, for example. Fractal Black, in general, for cryogenic applications, for deep space missions, for places where you might need some imaging telescopes for infrared, for example. And these are two key coatings that we offer for stray light mitigation, especially in space applications. They have a lot of heritage. They're well used, completely inorganic, as all of our coatings. And they provide a very uniform coverage on the instrumental parts to make sure that all the unwanted light is absorbed.
I also want to get a sense of not just the traditional big budget, big organization space missions, but also from a new space context as well. Are there also examples of new space contexts on small organizations, small startups, scaling companies also using this?
Yes, of course, especially since the new space era has really taken off. We have got a lot of inquiries for emerging startups who are started to be more established as well. And we see that there is a real need. So basically, if you look at the missions that we have participated in and all the applications, it's great. You can talk about space heritage, but what it really shows that there is a real need for Acktar coatings in the industry. And that need ranges from low Earth orbit through geostationary orbit to really deep space and Moon, Mars, and all kinds of applications where Acktar coatings, and they're multifunctional, and they're an all-in-one solution that can really satisfy the customer need. So whether if it's a small startup or an OEM, it will help both.
Tamas, I think it's been super interesting with all the insights out there. Every field, including materials, are changing because of the introduction of so many other things, including smarter materials, AI, and so many other things, right? So where do you see the next phase of stray light control going towards? And what are some interesting things that people should expect to see in the next 5 to 10 years?
That's actually one of my favorite questions, especially when you go to conferences and exhibitions, because you get to talk to experts and other people in the industry and share your thoughts. I can tell you the field is evolving fast, and let's go through some examples. So there are new materials, they are blacker, they are thinner, and they are broader in spectrum. Think about ultra black surfaces that absorb light across a broader wavelength range, or anti-reflective layers that are almost invisible. At Acktar, we are pushing both optical and the environmental performance boundaries. Look at integrated designs, right? Future systems will build stray light suppression into the optical design from the start, and it's critical. It means designing lenses and baffles and coatings together as one system. Compact, efficient, and powerful. At Acktar, we offer full turnkey solutions, like I mentioned. We manufacture the part and coating the service, but in some cases, it involves even a collaborative design effort in the engineering teams, which is really helpful to the product lifecycle. I talked about basically missions by rapidly changing environments, so like orbiters or rovers. In these cases, imagine a system that can monitor stray light levels in real time and adjust the internal optics to compensate for it. So it's like autofocus, but for light cleanliness. It's crazy what can be done. One of my favorites is nanotech and metamaterials. So this one is really cool. Scientists are developing nano-engineered materials that can bend or absorb the light in very specific ways. So imagine like a nano-engineered black surface that traps light at the microscopic level. They are almost like tiny forests that absorb light. And these could lead to surfaces that are nearly invisible to stray light, but very totally transparent to your signal. It's still early days, but there's a lot of potential. There is, of course, AI. We are living in the age of AI right now, and the development, and every day there's some new thing coming out, and computational imaging. So machine learning can autocorrect the stray light in the images, and machine learning and AI can also use the integrated BRDF data of Acktar coatings in the optical simulation software. So that's without a question very helpful. And one of the most important, in my opinion, is that currently there is a growing push for collaboration between space agencies and research teams and industry players. And when you share best practices and simulation tools and data, this really helps everyone get better faster. So we're going to start seeing more common standards for Strelite testing and design, which is great for reliability and mission planning. Collaboration is the name of the game. But to really wrap it up, instruments, they are getting more advanced, right? And missions are more ambitious. And Strelite control is kind of going from a background issue to the frontline design focus. And with smarter coatings, more integrated systems, AI, future of space optics looks clearer and sharper than ever. I can tell you that. And of course, darker where it needs to be.
A lot of interesting insights backed into all of this. We will link Acktar's coatings in this podcast episode so that people who are interested can have a deeper look at the specs and also maybe get in touch with you guys if they are interested in it. I thank you again for taking so much time and giving enough information to know why this is exciting and why Strelite is an issue and how it should be tackled.
Thank you for having me.
Thanks for joining me today for another exciting story from the space industry. If you have any comments, feedback, or suggestions, please feel free to write to me at info@satsearch.com. And if you're looking to either speed up your space mission development or showcase your capabilities to a global audience, check out our marketplace at satsearch.com. In the meantime, go daringly into the cosmos. Till the next time we meet.